December 6, 1957. A Vanguard TV-3 ignites on the pad at Cape Canaveral, rises 4 feet, loses thrust, and collapses into a fireball on live television. The press called it Flopnik. Engineers called it a fuel injector pressure loss. It became the most public failure in early space history, and it taught NASA a lesson about ground testing that would shape every program that followed. 67 years later, in the frozen desert of Inner Mongolia, history rhymed. A Tianlong 3 first stage ignited for a static fire test, broke its hold-down restraints, climbed inverted, and impacted the ground approximately 1.5 kilometers away. Different propellant, different nation, same fundamental problem. A ground test that became an uncontrolled flight. What the headlines won't tell you is that this is the second Chinese rocket to escape a test stand in under 2 years. That pattern points to a gap in ground support infrastructure, the boring hardware that SpaceX spent a decade perfecting at McGregor. Today, we're examining what Vanguard taught NASA about test stand design and whether Beijing learned the same lessons. So let's talk about what Tianlong 3 actually is, because the framing matters here. Media outlets are calling this China's Falcon 9. And while I understand the shorthand, that comparison assumes an architectural parity that doesn't exist yet. Tianlong 3 is a medium-lift kerosene LOX vehicle built by Space Pioneer, also known as Tianbing Technology. And here's the detail that gets lost in the coverage. This isn't a CNSA rocket. This is a private Chinese company operating in a fragmented commercial market, competing against other Chinese firms as well as the state apparatus itself. The vehicle uses a cluster of 9 THQ-12 engines on its first stage, generating approximately 820 metric tons of sea-level thrust. For comparison, that puts it in the same neighborhood as Falcon 9's Merlin cluster, though the specific impulse numbers tell a slightly different story. We're looking at an estimated 290 to 300 seconds at sea level for the THQ-12, compared to Merlin 1D's 282 seconds. On paper, that's competitive, but sea level ISP is just one variable in a very long equation, and the test stand is where that equation gets validated. This was supposed to be a qualification static fire, a standard gate in the development process before any orbital attempt. The vehicle was never supposed to leave the pad. It was supposed to light its engines, run for a prescribed duration, shut down, and provide telemetry that engineers would spend weeks analyzing. Instead, approximately 4 seconds into the burn, the first stage broke free and climbed. Now, here's where we need to separate what we know from what we're speculating. The vehicle lifted off, inverted during ascent, experienced engine shutdown, either through autonomous abort or structural failure, and then followed a ballistic trajectory to impact roughly 1.5 kilometers downrange. The explosion on impact was dramatic, but the engines themselves appear to have functioned. And that's the engineering paradox here. The engines worked, the thrust was delivered. The problem wasn't propulsion, the problem was restraint. There are 2 scenarios that fit the available data. The first is a hold-down clamp failure under thermal load. Inner Mongolia's desert environment sees overnight temperatures dropping to -15 degrees Celsius, and that kind of cold affects seal integrity, hydraulic fluid viscosity, and the mechanical tolerances of any restraint system. If the clamps were designed for nominal thermal conditions and the test was conducted at the edge of that envelope, you could see exactly this kind of failure. The second scenario is a thrust calibration error, meaning the actual thrust output exceeded the design margin for the hold-down system. If the THQ-12 engines delivered 10 to 15% more thrust than the specification predicted, clamps sized for nominal load would shear. And here's the detail that should concern anyone watching China's commercial space sector. This isn't the first time this has happened. In July of 2024, at a test facility in Gongyi, Henan Province, a different vehicle from a different company experienced the exact same failure mode. That rocket escaped its test stand during a 30-second qualification burn of THQ-12 engines and crashed into nearby hills. Same engine family, same restraint failure, same uncontrolled ascent. 2 incidents in 18 months isn't bad luck, it's a pattern. And that pattern points to one of 2 systemic issues. Either the THQ-12 thrust specification is incorrect across the entire Chinese commercial industry, or the ground support equipment standards being used by these companies are systematically undermargined for the loads they're expected to handle. This is where the heritage comparison becomes instructive, because we've seen this exact problem before, and not just with Vanguard. When the Soviet OKB-1 was developing the N-1 moon rocket in the 1960s, they faced a similar challenge. The N-1's first stage used 30 NK-15 engines, and the combined thrust during static fire testing exceeded what their initial hold-down bolt designs could handle. They experienced shear failures. They experienced thermal expansion issues in the Kazakh steppes' extreme temperature swings. And they solved it, eventually, through iterative redesign of their test stand restraint systems. But that iteration took years, and it happened within a single institutional framework where lessons learned on one test could be immediately applied to the next. China's commercial sector doesn't have that institutional continuity. Space Pioneer isn't sharing test stand data with Landspace. Galactic Energy isn't coordinating GSE standards with iSpace. Each company is essentially learning these lessons independently, and that fragmentation shows in the failure pattern we're now seeing. Here's my question for the engineers watching. Was this a clamp failure or a thrust calibration error? And if you've worked in cryogenic ground support equipment design, what's the thermal margin you'd spec for a negative 15 degrees Celsius desert environment? I want your analysis in the comments, because this is exactly the kind of failure mode where operational experience matters more than textbook theory. The deeper issue here isn't about one rocket or one company. It's about the infrastructure gap that separates where China's commercial sector is from where it needs to be. SpaceX has conducted over 3,000 Merlin engine tests at their McGregor facility since 2007. 3,000. That's 3,000 data points on hold-down clamp performance, on thermal cycling effects, on thrust measurement calibration. Every Raptor test informs the next clamp specification. Every anomaly gets fed back into the GSE design loop. That's not genius. It's just iteration at scale, and it takes time that can't be compressed. China's commercial firms are building test stands in parallel with the vehicles themselves. They don't have 15 years of institutional GSE knowledge to draw from. CNSA's experience doesn't transfer cleanly because the state program uses different engine architectures, different propellant combinations, and different test methodologies. So companies like Space Pioneer are essentially starting from first principles on ground support equipment while simultaneously trying to develop flight-ready hardware. And when you compress those timelines, you get exactly what we saw in Inner Mongolia, a vehicle that worked exactly as designed, restrained by infrastructure that wasn't ready for the load. Vanguard TV-3 rose exactly 1.2 meters before fuel injector pressure collapsed and the vehicle dropped back onto the pad. The Tianlong rose approximately 50 meters before inverting and following a ballistic arc to impact. Different scale, but the same category of failure. Both were ground tests that became uncontrolled flights, and both revealed systemic gaps in how their respective programs approached pre-flight qualification. Here's the misconception that's persisted for nearly 7 decades. Vanguard is remembered as a rocket explosion, a spectacular fireball that humiliated the United States on live television. But that framing misses the engineering reality. Vanguard TV-3 wasn't an engine failure in the traditional sense. It was a fuel system failure that caused loss of thrust, followed by structural collapse when the vehicle dropped back onto a fully fueled first stage. The explosion was a consequence, not a cause. The immediate trigger was a fuel injector leak that caused combustion chamber pressure to drop below sustainable levels at T+2 seconds. The engine shut down, exactly as it was designed to do when chamber pressure falls outside nominal parameters, and the vehicle, having barely cleared the launch stand, fell back under gravity. The fireball came from ruptured propellant tanks on impact, not from a propulsion system malfunction. But the deeper cause wasn't mechanical. It was schedule pressure. Sputnik had launched 2 months earlier, and the Eisenhower administration was desperate for an American satellite in orbit. That political pressure compressed the Vanguard test timeline in ways that the engineering couldn't support. The static fire campaign was abbreviated, hold-down test durations were shortened, and the vehicle went to the pad before the ground support infrastructure had been fully validated. The lesson NASA took from Vanguard shaped every program that followed. By the time Atlas was carrying Mercury capsules, the static fire protocol required a minimum of 30 seconds of sustained burn before any engine could receive flight-rated designation. That wasn't arbitrary. It was the institutional response to watching a rocket fail because the test campaign had been rushed. And when you look at what happened in Inner Mongolia, you see the same pattern. A vehicle that went to the test stand before the ground infrastructure was ready to handle the loads it would generate. While the Vanguard comparison gives us historical context, the more instructive parallel for understanding China's current gap is the difference between SpaceX's McGregor facility and what China's commercial sector is working with today. SpaceX has conducted over 3,000 Merlin engine tests at McGregor since 2007. 3,000. That's not just engine development. That's 18 years of continuous refinement of every piece of ground support equipment that touches those engines. The misconception I keep seeing in comment sections is that China can simply copy the Falcon 9 design and catch up. And from a vehicle architecture standpoint, that's partially true. The basic principles of a kerosene LOX first stage with grid fins and landing legs aren't classified, but copying the rocket is the straightforward part. Copying the test infrastructure takes decades because test infrastructure isn't a design you can reverse engineer from photographs. It's institutional knowledge accumulated through thousands of test cycles. Ground support equipment is what determines your test cadence, and test cadence is what determines how fast you can iterate on vehicle design. We're talking about hold-down clamp systems, whether you use hydraulic release or mechanical release, how you size the bolts for thermal cycling, how you account for thrust oscillation during engine startup. We're talking about thrust measurement load cells that need to accurately capture transient forces during ignition. We're talking about propellant feedline thermal conditioning systems that keep your cryogenic oxidizer at the right temperature during long hold-downs. And we're talking about emergency deluge systems that can flood the pad with water in seconds if something goes wrong. SpaceX's advantage at McGregor isn't that they have better engineers, it's that they have 15+ years of iterative GSE refinement baked into every test stand. Every anomaly they've encountered has fed back into the next design revision. Every clamp failure, every instrumentation glitch, every thermal surprise has made the infrastructure more robust. China's commercial firms don't have that institutional memory. They're building test stands in parallel with the vehicles themselves, and CNSA's experience doesn't transfer cleanly because the state program uses fundamentally different engine architectures and test methodologies. This is the same gap that Rocketdyne faced in the early 1960s when they were developing the F1 engine for Saturn V. The F1 produced 1.5 million pounds of thrust at sea level, an order of magnitude beyond anything that had been tested before, and the initial test stand designs at Edwards and Santa Susana simply weren't built for those loads. They had turbopump failures that scattered debris across the test complex. They had combustion instability that destroyed engines in milliseconds. And they learned, through painful iteration, that Saturn V's success would be built on test stand reliability as much as engine performance. You can't develop a flight-ready engine if your ground infrastructure keeps failing before you get useful data. Now, here's where the pattern recognition becomes critical. July 2024, Gongyi, Henan Province. A different vehicle, built by a different company, experienced the exact same failure mode we saw in Inner Mongolia. That test article escaped its stand during a 30-second qualification burn of THQ-12 engines and crashed into nearby hills. No injuries, but a total loss of the vehicle and significant damage to the test facility. The mainstream framing at the time was that this was a one-off accident, an unfortunate anomaly in an otherwise promising development program. But two identical failure modes in 18 months isn't an accident. It's a design pattern, and that pattern demands explanation. Both vehicles used engines from the same kerosene LOX family. Both test stands failed to restrain what should have been nominal thrust levels. The Gongyi incident occurred during a 30-second burn, well into the test duration. The Inner Mongolia incident occurred in the first 10 seconds. Different timing, but the same fundamental failure: restraint systems that couldn't handle the loads they were designed for. There are only two explanations that fit this data. Either the THQ-12 thrust specification is systematically incorrect across the entire Chinese commercial launch industry, meaning every company using this engine family is working from flawed baseline numbers, or the ground support equipment standards being applied by these companies are systematically undermargined for the actual forces involved. Neither explanation is reassuring, and both point to a coordination gap that doesn't exist in more mature space programs. This is where the Soviet experience becomes instructive, because Sergei Korolev faced exactly this problem in the late 1950s. The R-7, the world's first intercontinental ballistic missile, and the rocket that launched Sputnik, went through multiple hold-down failures at Tyuratam before the design team solved the restraint problem. The R-7's 4 strap-on boosters generated enormous asymmetric thrust loads during ignition, and the early test stand designs couldn't handle the lateral forces. Korolev's solution was elegant. Instead of fighting the thrust loads with brute force restraints, he designed a system that worked with the rocket's geometry. The R-7's distinctive Tulip petal structure holds the vehicle in a cradle that releases naturally as thrust builds. The rocket essentially lifts itself out of the support arms rather than breaking free of clamps. It's a design that's still flying today on Soyuz, 67 years after it first proved itself at Tyuratam. If you want the full breakdown of how Korolev solved the hold-down problem for the R-7 and why that design philosophy still influences launch infrastructure today, check out our deep dive on the sister channel. Link is in the description. The question facing China's commercial sector isn't whether they can build competitive engines. The THQ-12 appears to deliver the thrust and specific impulse numbers it was designed for. The question is whether they can build the ground infrastructure to test those engines safely and learn from each firing. Because without that infrastructure, every static fire becomes a roll of the dice. Space Pioneer had a 2026 orbital slot booked for Tianlong 3's debut flight. That slot is now in jeopardy, and understanding who actually loses here requires looking past the headlines about China's space program and into the fragmented reality of how that country's launch sector actually operates. The misconception I keep seeing is that this failure hurts China as a monolithic entity. It doesn't. This hurt Space Pioneer specifically, a private company that was already competing against other Chinese commercial firms as well as the state apparatus itself. And in a zero-sum market for payload contracts, one company's failure is another company's opportunity. China's commercial launch sector isn't unified. It's a collection of competing entities with different technical approaches and different funding sources. You've got Space Pioneer with their kerosene LOX Tianlong architecture. You've got Landspace with their Zhuke-2, which uses Methalox propellant and has already reached orbit successfully. You've got Galactic Energy flying their solid-fueled Series 1 for small payloads, and iSpace pursuing yet another development path. Meanwhile, CNSA maintains market dominance through the Long March family, and the commercial firms are essentially fighting over whatever payload contracts the state program doesn't want. This failure reshuffles that competitive landscape in ways that aren't immediately obvious. Landspace's Zhuke 2 just became more attractive to customers who were hedging between Methalox and Kerosene LOX architectures. Space Pioneer's propellant choice, which was supposed to leverage existing engine heritage, now looks like technical debt compared to Landspace's cleaner sheet approach. And any customer who was considering Space Pioneer for a 2026 or 2027 launch is now recalculating their risk exposure. We've seen this dynamic play out before in the American commercial sector. When Orbital Science's Antares rocket exploded seconds after liftoff in October 2014, destroying a Cygnus cargo spacecraft bound for the International Space Station, the immediate consequence wasn't just a delay for Orbital. It was a market share shift towards SpaceX, whose Falcon 9 was already demonstrating the reliability that commercial customers needed. Orbital recovered eventually, but they never fully regained the competitive position they held before that failure. The launch market has a long memory, and customers optimize for schedule certainty above almost everything else. Now, while the commercial competition angle matters for understanding who wins and loses in the near term, the bigger strategic question is what this failure means for China's Constellation ambitions, because that's where the timeline pressure gets existential. 13,000 satellites. That's the Guowang filing with the International Telecommunication Union. Guowang is China's answer to Starlink, a low Earth orbit communications mega-constellation designed to provide global broadband coverage and reduce China's dependence on Western satellite infrastructure. And every single one of those 13,000 satellites needs a ride to orbit. The misconception I hear constantly is that China will simply use Long March rockets for Guowang deployment, and technically they could. The Long March family is reliable, flight-proven, and available. But Long March can't close the business case. Expendable launch costs make mega constellations economically impossible at scale. Let's run the numbers. Starlink's deployment economics work because Falcon 9 is reusable. SpaceX can launch 60 satellites at a time, land the booster, refurbish it, and fly again within weeks. Their effective cost per kilogram to low Earth orbit is somewhere in the range of $1,500 to $2,000 when you account for booster reuse. An expendable Long March 5, by contrast, costs somewhere north of $10,000 per kilogram, and you're throwing away the entire rocket every flight. At those economics, deploying 13,000 satellites becomes financially ruinous. Guowang doesn't work without reusable launch capacity, which means Guowang doesn't work without vehicles like Tianlong 3 or Landspace's in-development Zhuke 3. CNSA's own reusable variant of the CZ-10 isn't expected to be flight-ready until 2027 or 2028 at the earliest, and that timeline assumes no development delays, which, per our standard framework, means you should probably add another 18 to 24 months to any official projection. Each commercial reusability failure doesn't just delay one company's orbital debut, it delays the entire Guowang deployment timeline, and that timeline is running against a competitor who's already deploying satellites by the hundreds every month. If no Chinese reusable vehicle is operational by 2027, Starlink's orbital slot advantage becomes insurmountable. There are only so many frequencies and orbital positions available for LEO constellations, and the ITU filing system rewards operators who actually deploy hardware. SpaceX is filling those slots right now. Every month that China's reusable capacity stays grounded is a month where Starlink extends its lead in orbital real estate that can never be reclaimed. This is the same trap that killed Iridium the first time around. The original Iridium constellation filed for bankruptcy in 1999, less than a year after completing deployment, because the launch cost assumptions that underpinned the business case didn't hold. They'd budgeted for a certain cost per satellite to orbit, And when actual launch costs came in higher and deployment took longer than planned, the economics collapsed. Constellations live or die on launch economics, and right now, China's launch economics for mega constellation deployment don't work. So what happens next? Based on historical recovery timelines from comparable failures, expect a 9 to 14-month delay before Space Pioneer attempts another integrated static fire of a Tianlong 3 first stage. That's not pessimism. That's just how these investigations work. The misconception is that China will simply cover this up and move on, the way state programs sometimes do with embarrassing setbacks. But Space Pioneer isn't CNSA. Private companies can't bury failure reviews because investors and insurers require them. If Space Pioneer wants to continue raising capital and securing payload contracts, they need to demonstrate that they understand what went wrong and have implemented corrective measures. That process takes time. The likely sequence looks something like this. First, a formal anomaly investigation, 60 to 90 days minimum to review telemetry, inspect debris, and establish root cause. Then, GSE redesign and requalification, 6 to 9 months to address whatever hold down or thrust calibration issues caused the restraint failure. Then, a single-engine test campaign to validate the fixes before attempting another full-stack static fire. Stack all that up, and you're looking at a realistic orbital attempt in Q4 2026 at the absolute earliest, and probably later. Watch for two secondary effects in the coming months. First, CNSA publicly distancing itself from commercial sector failures to protect the Long March brand reputation. Second, potential regulatory tightening on private test operations, especially anything conducted near populated areas. That village 1.5 kilometers from the impact site is going to factor into policy discussions. For comparison, when SpaceX experienced the Amos 6 pad explosion in September 2016, a catastrophic failure during a routine pre-launch static fire that destroyed both the Falcon 9 and its payload, they returned to flight in just 4 months. But SpaceX in 2016 had nearly a decade of institutional knowledge about their vehicle and their ground infrastructure. They knew exactly where to look for the anomaly, and they had the engineering depth to implement fixes quickly. Space Pioneer doesn't have that institutional foundation yet, and building it takes time that the Constellation clock isn't giving them. Here's the descent path. This failure isn't about one rocket. It's about ground infrastructure, the test stands, the clamps, the thermal margins that take a decade to get right. Vanguard taught America that lesson in 1957. SpaceX learned it at McGregor over 3,000 engine tests. China's commercial sector is learning it now, the hard way. The question isn't whether they'll recover. They will. The question is whether they'll recover fast enough to matter in the Constellation race, and right now, that clock is running against them. This has been Go for Powered Descent. I'll see you on the next mission.